So far in class, we've been looking at rate laws, and a rate law typically looks something like this. So we've got some expression, rate, and this is related to changes in concentration of, say, A with changes in time. And the rate law basically is an equation that says that if we know how, say, the concentration of A is at any point in time, if we know the rate constant, we can calculate the rate. And so, of course, we know that if we're running these kind of reactions, if A is a reactant, then with time, the concentration's looking something like this. Okay? We know that for all reactions, reactants are going to go down in concentration until they reach a value of 0. And the rate law gives us an opportunity to figure out how fast this is going on. And if you look at the expression up above, you can see this is basically equal to the negative of the slope. And so at any point we can calculate the rate by just calculating, I guess, changes in concentration of A and changes in changes in time, and dividing and flipping the sign. And of course we flip the sign because we don't like negative rates. Now, the big problem is, although sometimes it's really nice to know at a particular time, if we've got a concentration of A, how fast is the reaction going, normally what's more useful is knowing how on earth we can predict what A will be at, say, 10 seconds, 30 seconds, 2 minutes, 2 hours, what have you. So we really need a way to figure out how on earth to figure out the concentration with time. So how are we going to do this? Well, let's say we've got a reaction, and the stoichiometric equation is A goes to P. And so we can write down the rate of this reaction. We can just look at either the change in concentration of A with time, and we could also look at the change in concentration of products with time. And remember that we adopt the sign convention that rates are always positive. So reactants are going down in concentration, so we multiply it by a negative number to get a positive rate. If any coefficients in our equation were something other than 1, we would need to divide these rate expressions by the coefficient. Now, let's say it's first order, and remember rates are determined experimentally, or rate laws are, so we can't really look at this and say it's first order, but if it was, then we can write down the rate expression. So it's K, the rate constant, times by the concentration of A to the first power. And so this is first order with respect to A and first order overall. Now, if we wanted to, we could equate those two terms. So we could look at the change in concentration of A with time, and we could say, well, that's the rate. That's experimentally what we've got to measure to get the rate. And we could also take our rate law, and our rate law, if it's first order, notice there's a lot of ifs here. We don't necessarily know it is at this point. Looks something like this. So it's K times A to the first power. So what this tells us, of course, is basically it's a recipe. It's a machine. And the machine says if you squeeze A, if you put the concentration of A, squeeze it into this expression, and multiply it by K, I'll give you the rate. Or if you like, I will give you the change in concentration of A with time. And so if we ever know the concentration, we can find the rate of the reaction and we can predict it. And again, that's really super duper cool, but it would be totally awesome if we could figure out how to predict what the concentration will do at any time. And those of you who've had some calculus will be happy to know that there's actually a point to all of that calculus, and we can go ahead and derive an expression. I'll go ahead and spend a couple of minutes and derive an expression. Feel free to completely fast forward past this if you want to. Okay, so let's say you know some calculus and you're dangerous and you want to use your calculus here. Okay, so how are we going to do it? When we know the rate is minus change in concentration of A with time, and we know that for a first order reaction that's equal to K times the concentration of A. Now we're cheating a little bit actually, and so the changes in concentration, those are large changes, and in order to use some calculus we've got to make them small changes. And so the standard notation here is to use the d symbol for teeny tiny little changes. And so we can rewrite this as minus dA dt is equal to k times the concentration of A. Now, we can do something very naughty here. We can pretend like this is a fraction, and we can get all the A's on one side and all the T's on the other side. And so we can make this say minus dA, and we can take that lonely old A over there and we can bring it to the left-hand side. And we can take the T and we can throw it over to the other side. And we can also drag the minus sign over, and we have an expression that looks something like this. So what we've done, this is called separation and integration, and we've done the separating part. We've got two things that can change. We've got concentrations of A, and notice all those terms are on the left, and we've got time on the right. And our rate constant, well, it's a constant. We can chuck it on any side of the equation we want, and everything will be hunky-dory. Now, for the fun part. We've separated so we can integrate. So we can take both of these expressions here, and we can draw our red integral, and we can integrate between initial and final limits. Now, the left-hand side, that's concentration, and so it probably makes sense to define an initial concentration, A sub 0, and a final concentration, we'll call that A sub t. On the right-hand side, we've got time, and so we can go ahead and go from 0, the start of our experiment, and t, whatever time we stop the experiment at. Now, the math department will be very mad at me here, because I've used t for both a variable here and an integration limit here. And they would probably want you to prime one or the other. We'll say, who cares? The right-hand side's not so bad. Actually, since k is a constant, it can be brought out front. And then we got the integral of dt. The integral of dt is just t. And we've got it between the limits of 0 and t. And so that means that it's minus k. And then we take t equals t and t equals 0 and subtract 1 from the other. So that's t equals t, t equals 0. And of course that gives us minus kt. Now what about the left-hand side? The left-hand side, in case you're stressing out here, we've got the concentration of A. But of course, the concentration of A, we could call x. And so if we had dx over x, or you might prefer to write that as 1 over x dx, you should start to get excited now. This looks like one of those standard integrals the math department loves. And if you remember, the integral of 1 over x dx is the natural logarithm of x. Now, this is an indefinite integral. We got a constant of integration. For a definite integral, those c's would cancel off as we put in the upper and the lower limit. So now the left-hand side is the natural logarithm of x, where x is the concentration. So we can go ahead now, and we're almost there actually. And so we can now say it's the natural logarithm of A between the limits of initial concentration A0, final concentration A sub t, and that's equal to minus kt. And we can do some tweaking here. We can say it's the log of the upper limit, A sub t, minus the natural logarithm of the lower limit, A sub 0. And all that's equal to minus kt. Now, one of the cool things about natural logarithms, and any logarithm, is that the log of A minus the log of b can be rewritten as the log of a divided by b. So that means then the left-hand side, when we got the log of one thing minus the other, we could write that as the log of the one thing divided by the other. And at this point, we've got what we call the integrated rate equation. Why integrated? Well, we had to go through and separate and integrate to get the expression. All right, if you haven't taken any calculus, you don't have to really worry. I'm just going to go ahead and flip to the next slide and rewrite this expression for you.